So welcome to MathStat 341 probability. This is lecture 11. And so what we're going to do now is we're going to start introducing some of the big theoretical concepts that we're going to be working with. So we've spent a lot of time motivating the material. We've seen a bunch of problems that we can attack using various probability concepts. Now we're going to build up the theory to really explore them. The lecture is going to be changed a little bit based on the Sox destroying the Yankees last night. I'm actually having a discussion, does Yankee Elimination Day hold only during the day that the Yankees were actually eliminated? Or is it like Jewish holidays? Is it 24 hours from when the sun goes down on the Yankee season? I think it's 24 hours. So we're celebrating Yankee Elimination Day today. And I had a question that I sent to some of my colleagues, including some of the people who are working on the GOAT project with us. And if time permits, we'll talk about that as another research question that people can get involved in terms of writing a paper. It's related to high school tennis and golf matches. Okay, so for what I want to do today, just going to get things to advance, is I want to talk about the basics of PDFs, probability density functions or probability distribution functions, and maybe a little bit about the cumulative distribution functions as time permits. We'll talk a little bit about continuous random variables versus discrete random variables. How many of you have taken a class in multivariable calculus? Okay. Given that this is a prerequisite for probability, this is really good that everybody has taken multivariable calculus. We don't use it that often. Most of the time, the integrals we use are just two copies of one-dimensional integrals, but there are occasional times when it's useful to have. How many of you have taken an advanced class in summation theory? Yeah, now no hands are going up. We don't have as good formulas for sums as integrals. And this is why we model a lot of things with continuous random variables rather than discrete random variables, because we can do a lot more with the continuous stuff. We have the fundamental theorem of calculus. And again, with the fundamental theorem of calculus, the meat is that the area under the curve is the antiderivative of B minus the antiderivative of A. And it turns out that the area often denotes probabilities. We'll talk a little bit about moments and expected values. We've seen them already a little bit with the German tank function. We'll make it a little bit more explicit as to what we are looking at and why. This will be a little bit related to Taylor series later in the semester. And so I'm going to quickly review a little bit of Taylor series. I'm going to teach a trick on how to do multivariable Taylor series very quickly. If you haven't taken a class with me, odds are you probably haven't seen this trick. It should be more widely known than it is. And I always like the opportunity to just show you how to avoid having to do the very messy. All right, so it's d squared f dx dy. Is there a factor of a 1/2 in front of that or not? You're trying to remember what is the multivariable Taylor series expansion. There's a really nice trick that gets you around a lot of that. I'm going to put up a little clip to some more coding, and the code files and the PDF are there as well. This is also on the home page. The more coding you do, the better. It's just a really good skill to have. All right. So the first thing I want to talk about is probability density functions. So we have some random variable x. So x is a random variable. And we usually use capital letters to denote a random variable, and we usually use lowercase letters to denote the value of the random variable. Typically in books, they do it in boldface. Sometimes when you're writing things, you do it, maybe dark, strange letters and whatnot, because we can't do boldfaces either. Like you might have seen, the real numbers and the complex numbers written like this. That's really done because we can't do boldface. If you're writing it in a book, you can do boldface, so you really shouldn't have to do that. But people have just adopted and they just use that now. I will try to always make it very clear with my messy handwriting when something is a random variable by making it hopefully look like a cap. And that's why I'm going to put the big lines over x and y. So x is a random variable. So we have a density either p or f or p sub x or f sub x. So why do you think we might use the letter P? Probability. If we have many different random variables in play, it's nice to have a subscript so we can quickly look down and say, this is the density associated to the random variable X. If there's only one random variable that's under discussion, then we might as well just write it as F, just for brevity. But when things get more and more involved, it's nice to have a subscript so you can quickly look down. We often use f for functions, so that's fine. So we need, f of x to be greater than or equal to 0 for all x. And we need the integral from -infinity to infinity of f of x dx equals 1, or the sum and goes from 0 to infinity of f of xn equals 1. So the first case is obviously the continuous case. The second case is the discrete case. You could, of course, have a third case where the density is continuous in some parts and discrete in others. So maybe I have a 50% chance of getting the value of 1, and then a 50% chance of taking a number uniformly in the interval 0, 1. And so my interval, my possible values would be between 0 and 1, but it'll be a mix of discrete and continuous. So we can handle stuff like that as well. And then if we want, the probability that A is less than or equal to big X less than or equal to B. So this is the probability we take on a value between A and B. This is equal to the integral from A to B of f of x dx, or it's the sum A less than or equal to xn less than or equal to B of f of xn. Now, there are some advantages between continuous random variables and discrete random variables. What's the probability, if you have a continuous random variable, of taking on exactly the value 3? 0. In fact, it doesn't matter what value I give you. Any value on a continuous random variable, the probability you take on exactly that value is 0. For a discrete random variable, however, there could be real probability. So when I'm integrating, I can actually be a little bit careless about the endpoint. Do I include it or not? If it's continuous, it doesn't really matter. If it's discrete, it does matter. Now, this leads to a very famous problem in probability. And I do have a dartboard if anybody wants to actually test this. So I have a dartboard and I throw a dot at it. What do you think the distribution of where the dot lands at? I'm the one who's throwing it. Wow, thank you. So you have absolutely no respect for my dot abilities. You're not going to say, oh, Professor Miller, 100% hitting the center.
Well, you said keep in mind you're throwing.
Yeah. That's fine. That's fine. We've got personalized exams. Okay. So we'll assume uniform distribution. I would at least hope that maybe some kind of radial decay, maybe a little bit more likely towards the center, but we'll assume uniform distribution.
That sounds hard. Let's do uniform.
We'll do uniform. All right. So now, what's the probability that the dot lands at any point? 0. But the dot has to land somewhere, right? So what does it mean to say the probability that the dot lands at any point is 0, yet the dot has to land somewhere? One way people interpret this is saying the probability that, if you keep doing this, that it ever lands at the same point twice is 0. The other thing is, and we skipped this section, is we have to be very careful about what events we talk about. And so what we really want to do is we want to talk about what is the probability, for example, that the dot lands in a small little square like that. And we can talk about something like that. It's going to just be the area of the red square divided by the area of the circle. And that would be the probability we land. So it's, what events we assign probabilities to. So what events, get probability. So here it would be area of red divided by area of circle. And so we'll have some kind of smeared probability distribution. If you think about what's going on in the real world, it's very unlikely we're doing anything with complete continuity. If you want, at some point, take a class in quantum mechanics, and you'll see that eventually there's some kind of scale length at which we're going. But it's technically easier to imagine that we have continuous random variables. All right, so this is the basics. And then the question is always, what can I do? When can I actually evaluate integrals like this? And this is why we have a whole slew of special distributions. If you have a name, you are probably a distribution worth knowing. Right? And there's a lot of distributions that have names, that have quantities that are very easy to work with. And so we try to model things by them because we can then do a lot and get close form answers. Worst case, you can often resort to numerics and computations. All right. So one thing we could do is we could try to find the probability distribution of a random variable in terms of another random variable. So for example, let's say X is uniform on 0, 1. So this means the density of X is equal to 1 if 0 less than equal to X less than equal to 1 and 0 otherwise. This is really the easiest continuous random variable I can give you. Yeah. Its density is constant. It's just 1. It's on an interval of length 1. And now I want to look at a nice random variable that's a function of X. Let's try y equals X squared. What is the density of y? Okay, so this is a very natural question to ask. If I square my random variable, it makes sense that I should be able to explicitly write down what the density is of the new random variable, knowing the density of X, because they're related in a very well-defined manner. The question is, how explicit can I make it? And one of your homework problems due this week, I believe, is one of my favorite problems in the course, which talks about if you have a random number generator that generates, I think, uniform random variables, how can you use this to generate other random variables? This means that you only have to make one random generator to get a whole slew of them. It's very similar to if you know logarithms in one base, you know logarithms in other bases. All right, so we're going to use what's called the CDF, the cumulative distribution function. So the CDF of X at little x is the probability that big X is at most little x, which would be the integral from minus infinity to little x of fx of t dt. So it's the probability of taking on a value at most x. So probability is at most little x. Okay. What do you think is true about this function? What do you think happens to this function as little x increases? Almost. It increases or stays the same. The probability is not going to go down. If my probability was 60% that I'm at most 2, it's still going to dip to 40% that I'm at most 7. So it's non-decreasing. And what do you think the limit as little x goes to infinity of the CDF of x is? 1. So we often write big F of x of little x to be the CDF of x at x, which is the integral from minus infinity to little x fx of t dt. So this is good notation. Why is this good notation? Well, if I take the derivative, that's going to be little fx evaluated at x. So what do we know about when I'm writing big F? Big F is what? How is big F related to little f? Right. So big F is the antiderivative of little f. And there's one word that is not good in the sentence. So what is the word I should change?
Is.
Nope. The. Right? We should get rid of the. what should we put in place? A. It is a, actually, we should practically do that. But this is a math class, not an English class, so we can deal with that. It is an antiderivative because there's more than one antiderivative. But of course, we know that big F of x has to go to 0 at negative infinity. But the limit as x goes to negative infinity of big F of x equals 0. So the is okay actually. Because there is a specific antiderivative we're doing. The probability has to go to 1 at infinity. It has to go to 0 at negative infinity. So there really is a unique antiderivative. But this is why we're using the notation big F for the cumulative distribution function. We're using this notation because when we are looking at what happens when we take the derivatives, it's going to be taking the derivative of the integral. Well, that's just going to give us the integrand. And again, remember, we're integrating from negative infinity to x. So really what this is the antiderivative of little f at x minus the antiderivative of little f at minus infinity. And when we take the derivative of a constant is 0. And so this is just one of the versions of the fundamental theorem of calculus. All right, so how can we use this to help us? So again, explicitly, if say big F prime equals little f of x, then the CDF of x at little x is the integral from minus infinity to x fx of t dt. It's the antiderivative at little f minus the antiderivative at negative infinity. So the derivative of the CDF, this is just writing down explicitly what I was saying, is just going to be big F prime of x. And this is just a constant. But this is just going to be little fx prime, little fx of x. And this is just justifying what I was doing on the previous page. This is just writing it down very slowly. So again, always try to think about what notation we're using and why. So returning to, let's let y equal x squared with x uniform on 0, 1. So we can calculate the cumulative distribution function of y. This is the probability big Y is less than or equal to little y. Well, what do we know about big Y? It's x squared. So we get, this is the same as the probability that x squared is less than or equal to little y. What does it mean for x squared to be less than or equal to little y? So if x squared is less than or equal to little y, then so what must be true about x if x squared is less than or equal to little y? Right. So if x squared is at most little y, what's true about x? I'm sorry? So say it again. X is at most little y? Not necessarily. X squared is less than or equal to little y. Let's say I have x squared. X squared, x is less than or equal to square root of y, right? If x squared is less than or equal to y, then the square root of x squared is less than or equal to the square root of y. Remember, 1/2 squared is less than or equal to 1/4, but 1/2 is not less than 1/4. So just because x squared is less than y doesn't mean. Now, when you said x is less than or equal to the square root of y, you are correct for this problem, but in general, there's something else you have to remember. Absolute value. Or just writing another way, the probability negative square root of y less than equal to x less than equal to square root of y. So if I do it like that, everything is fine. Because I have to remember when I square something, negative, I've got to be careful. But since it's uniform, this is going to be the probability 0 less than equal to x less than equal to square root of y, as x is uniform on 0, 1. So when we want to evaluate this, it depends on the value of y. If y is negative, okay, we're clearly not doing this. What value of y is it really easy to evaluate this? So 1, or in fact, anything greater than 1. So if y is greater than 1, what's the probability? No, 1. So the probability, x is between 0 and 1. So as long as y is greater than 1, the probability is just 1. So this is equal to 1 if y is greater than or equal to 1, the square root of y if 0 less than or equal to y less than or equal to 1, and then 0 otherwise. So we now know the cumulative distribution function of y. So we know the CDF of y, and now you can see why I like putting in all the different subscripts. So now we can actually get the density of y by differentiating. So the density of y is equal to the derivative of its CDF. And that's going to be what? It'll be 1/2 y to the negative 1/2 if 0 less than or equal to y less than or equal to 1 and 0 otherwise. And then you always want to check and see if this answer is reasonable. So what check should we do? The PDF is what? So if this is supposed to be a probability distribution, it should have two properties. What's one property probability distribution must have? So the area under the curve is 1. So that's the harder one to check. If you integrate this, you will get 1. So PDF, but it's also supposed to be non-negative. Is non-negative, integrates to 1. And both are true here. That doesn't mean we haven't made a mistake, but it at least passes a quick smell test. Yeah. If we had something that was negative, we might have done a derivative wrong. But notice how easy it was to calculate the distribution of x squared, knowing the distribution of x. And so this is called the CDF method. So this is the CDF method. Absolutely wonderful technique. Okay, any questions on the CDF method? So now we've reduced a bunch of problems to just finding derivatives. One thing that is probably worth noting, I'll just make this an observation. So when we're using the CDF method, in the CDF method, do not need big F of x, as only its derivative emerges. So more generally, we could look at, in our last example, we had the probability, 0 less than equal to x less than equal to square root of y. This would have been the cumulative distribution function of f at the square root of y minus the cumulative distribution function of x at 0. And this is a cumulative distribution function of y1. That's what we had. Now we then just use the fact that it's a uniform distribution, so this is equal to square root of y. But more generally, we would get then the derivative of the CDF of y, which is y's density, is just going to equal the derivative of the cumulative distribution function of x times the derivative of the square root of y. And that's going to just be the density of x at the square root of y, and in this case times 1/2 y to the negative 1/2. So do not need big F of x explicitly. This is good as integration is hard. Like if we actually had to calculate antiderivatives, then this may not be a great method, because I have to really work to give you a function that you can integrate. But what is wonderful is we first integrate and then we differentiate. So we almost return to where we started. The only reason it's not quite is because of where we're evaluating it. We then use the chain rule. That's okay. But the point is we never explicitly have to evaluate things such as the antiderivative of the density of x. We never have to calculate big F of x. And that's why this method can work. Okay. So as an example, I gave you in the function f of x equals 2 plus 3x minus 5x squared for x in 0, 1. And so the question is this a probability distribution? So we have to check two things. Is it non-negative? Does it integrate to 0? Does it integrate to 1? And so what I want to do is I want to just talk to you a little bit about curve sketching. This is a technique that was taught when I was young. It's not taught nearly as much, but it's worth seeing a little. So here's x, and underneath it, I'm going to write f prime of x. So if f of x is 2 plus 3x minus 5x squared, f prime of x is going to be 3 minus 10x. Okay. So the 2 points I care about, 0, 1, because I'm looking at my function in the interval 0, 1. What's f of 0? Two, right? No. If I'd done things better, I would have had it, equal like the Red Sox Yankees score. All right, so f of 0 is 2. What's f of 1? Is 0. So when I'm plotting it, I know it looks something like this. Now, if I look at f prime of x is 3 minus 10x. What is the critical point? So critical point is f prime of x equals 0. So 3 minus 10x equals 0. So x equals 3/10. If x is less than 3/10, what can you tell me about the derivative? It's positive. And what can you tell me about x that is greater than 0.3? What's your derivative? Negative. So when I'm doing my curve sketching, I know the function has to look something like this. It's got to be increasing until I get to 3/10 and then decreasing down to 0. So clearly my function will have to be positive in the whole region. I could have done other things to try to understand 2 plus 3x minus 5x squared, but this is the power of curve sketching. By looking at the sign of the derivative, I can tell is my function increasing or decreasing, and just by checking 3 points, I now know exactly what the function looks like. So the next thing is, does it integrate to 1? So let's look at the integral from 0 to 1 of 2 plus 3x minus 5x squared dx. So this is going to just be 2x plus 3x squared over 2 minus 5x cubed over 3, evaluated at 0 and 1. Well, I don't really have to worry about what happens at 0 because everything is just 0. So when I put in x equals 1, I get 2 plus 3 halves minus 5/3. So the common denominator is 6, right? So I would get 12 plus 9 minus 10 over 6. It's 11/6. So is it a density? No, so it's not a density. But 6/11 times f of x is a density. So it turns out it's not a big deal if you don't integrate to 1. You know, as long as you're non-negative and you have a finite integral, we can always fix it. So if you are if f of x is greater than or equal to 0, and the integral from 0 to negative infinity to infinity of f of x dx is finite, then g of x equals f of x divided by the integral from minus infinity to infinity of, say, f of t dt is a probability density. So we're basically just renormalizing. Of course, if the integral of f is 1, there's no need to renormalize. We're already a probability distribution. So the more important condition is to have something that's non-negative. If it's non-negative and integrates to a finite number, I can always adjust it to make it a probability distribution. We are going to use this observation many, many times later in the semester. I always love it when my teaching load aligns and I'm teaching both probability and complex analysis in the same semester, because one of the biggest results in both of these classes is how to integrate without integrating. And so we'll see how to do multivariable integrals without actually integrating. So how many of you remember your spherical change of variable formula? I actually remember 2 of them because the physicists and the mathematicians have slightly different notation. There's also generalizations to n dimensions. So how many of you have seen n-dimensional spherical coordinates? You can only imagine the joy of integrating in n-dimensional spherical coordinates. And we're going to basically bypass that by saying, well, look, I know the functional form and I know something's a probability distribution. Therefore, the constants have to work out so that it integrates to 1. And it'll be amazing how often we can bypass painful integration. So this is something we will do in greater detail later. All right, so continuing, we can talk about sums of independent random variables. So for example, imagine I have 2 fair die and I roll them and I add the numbers. So what are the possible outcomes if I have 2 fair die for the sum? Almost 2 through 12, right? So the sum 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many ways can I get a 2? Right, I can only have 1, 1. And similarly, 12, I can only have 6, 6. How about a 3? 2 ways. So I could have a 1, 2 and a 2, 1. And similarly for 11, I could have a 5, 6 or a 6, 5. For 4, I could do 1, 3. I could do 2, 2, or I could do 3, 1. And for 10, I could do 4, 6, 5, 5, and then 6, 4. And what you'll notice is it's basically a triangle. And so in this case, I can actually calculate, and as an exercise, write down a formula for the sum of two independent pair die. So we know it is, your fx of 7 is 1/6, fx of 2 equals fx of 12 equals 1/36. Because there's 36 possibilities, so I'm just counting them up. Is there a nice, clean way to write that? And there is. I think it's in the book, but try to think about that. This simple example shows you that if I have two random variables and I add them, it's quite likely that the new distribution is going to be very different. And it's a nice exercise. You could then say, well, what if I added 3 die or 4 die? It turns out it's a lot easier to look at a power of 2, because then you can just keep grouping it. So if I know the sum of 2 die is a triangle, and the sum of another 2 die is a triangle, and if I do 4 die, it's triangle plus triangle. And so that actually simplifies things a lot. In many things in math and engineering, we do things in powers of 2. All right, so what I want to now do is quickly define moments and expected values of random variables. So I have, as always, my random variable x. It has density f sub x. And then the kth moment is the integral from -infinity to infinity of x to the k times fx of x dx. Of course, everything I'm doing, you could also do for discrete random variables. And instead of integrals, what would you have? Summation. And so if you take classes on measure theory, they define what's called a measure so that you can use just one notation and handle both of them simultaneously. Really doesn't make much of a difference. So the hope is if no moments, know the moments, no f of x. So if I know the moments, the hope is that that would be enough to determine what my density is. Unfortunately, that's not the case. Analysis is hard. And I don't know if we've seen this function before, but if you look at the function g of x is e to the negative 1 over x squared if x does not equal 0, and 0 if x equals 0. If you plot it, it looks something like this. It's infinitely differentiable. If you use L'Hopital, so we'll do that for extra credit, you can show that any derivative of g at 0 is 0. This should terrify you. I have a function that's infinitely differentiable. At time 0, you're 0 units from home. Your speed is 0. Your acceleration is 0. What is the rate of change of the acceleration called?
Like the jerk.
Yes, it is the jerk. So email me for physics cultural credit, right? If you are calling someone a jerk, you're really making a comment about their rate of change of acceleration. Anybody ever, looks at you and asks? I don't know what the rate of change of the jerk is called. Is it? So send me a link for cultural extra credit. That is wonderful to know. Usually we don't talk about things beyond the 4th derivative, but there are names for stuff like this. So doesn't this bother you if all of your derivatives are 0, but you're not identically 0? This should not be. And this is why real analysis and probability is so hard, is that functions like this exist. When you do things in complex analysis, it turns out if you're differentiable once in complex analysis, you're differentiable infinitely often. You have a Taylor series that converges to your function wherever you're defined. So not just at the origin. It's really not that impressive that it agrees at the origin, because when I write it out as a Taylor series, I'm trying to do g of x versus g of 0 plus g prime of 0 times x plus g double prime of 0 over 2 factorial x squared plus dot dot dot. Well, no shit that it matches up when I take x equals 0, because I'm writing this side as g of 0 plus a multiple of x, which vanishes. So you have to agree at x equals 0. But amazingly, that's the only point where it agrees, even though the infinite sum converges. Instead of looking at the moments, which is x to the k, we could more generally look at, say, the expected value of g of x for some function g. Or maybe I should use a different letter because we're using g over here. So I'll use maybe the expected value of h of x would just be the integral from minus infinity to infinity of h of x times the density dx. And in the moments, h of x is just x to the n. So the moments are just a very special case. And the hope is that if you understand the moments or understand the distribution, it's not enough to just understand the integer moments. Okay, any questions on the definition of moments? They're still going to be useful. When you meet somebody as a freshman, what's the first thing you ask them? Okay, I would go name first, then where from. What's next? Entry. What do you want to major in? I think those are the four things. Do you play a sport? Do you do an extracurricular? It's the same thing when you meet a probability distribution. First thing you ask, what you mean? What's your standard deviation? And then you can start asking about the third and the fourth moments if you really want to get to know it well. Right? But these are the natural things to ask. And they start giving you the shape, they start giving you a feel for the object. All right, so I just want to briefly mention, so we've been talking about Taylor series. If I give you, for instance, say f of xy is cosine x squared plus xy squared, and you want the Taylor series. The normal way you would do this is you would have to find the partial derivatives with respect to x, y, with respect to x twice, x and y twice, and going on and on and on. Here's a beautiful trick. We know the cosine of u is 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial minus u to the 6th over 6 factorial, and so on and so on. So the cosine of x squared plus xy squared is just 1 minus x squared plus xy squared over 2 factorial, and I've got to square this up top, plus x squared plus xy squared to the 4th over 4 factorial minus dot dot dot. And that's a really fast way to calculate the Taylor series. So if I can view it as a function of one variable and then just substitute in that variable, now you have to do a little bit of work here. If I want to find the Taylor series, when I look at x squared plus xy squared, the x squared is degree 2, the xy squared is of degree 3. So when I expand this out, I'm going to get a term of degree 4, a term of degree 5, and a term of degree 6. And so there's going to be lots of different things that can contribute. So this is just a bad example in terms of how painful it can be. But because if I want to find all the terms of order 4, I can just stop over here. But this will give me some terms of degree 5 and 6. This one over here will give me terms of degree 8, and then et cetera, et cetera, et cetera. So you can have some interactions between various things. If I gave you a simpler one, it wouldn't be as bad. Another one I just wanted to briefly mention is, what is the volume of a sphere of radius r? And what's the surface area? So what is the area of a circle of radius r? Area. So note the derivatives. So this is a nice way to just remember these formulas. The surface area is the derivative of the volume. The perimeter is the derivative of the area. One way you can see this is if you imagine, what would happen if you increase the radius by delta r. If you increase the radius by delta r, this band should roughly be of size perimeter times delta r. And so when you then are differentiating, that's roughly where it should come from. Same thing for the spherical. So these are just ways to just try to remember various things. Right. Any questions on what we've done up till now? Okay. So this is from an email I got this morning. A colleague of mine loves how I can turn anything into a research question. And so here was the comment I made. And again, you could argue this is rationalization. You give me anything and I will find a way to justify it. I think it's actually really good that the Red Sox are the wild card team and playing Tampa, because Tampa has rested their pitchers and aligned their rotation. And the Sox rotation is now a little bit short because they had to win this do or die game. And so now you may have the situation where Tampa's number one pitcher does not go against our number one pitcher. And then we might be able to put our number one pitcher maybe against their number two pitcher or something like that. We may not be able to do that just because of how things align. But a lot of times in high school, in golf or tennis, the way it often works is it's 1 versus 1, 2 versus 2, 3 versus 3, say 6 versus 6. Has anybody played a high school sport with something like this? Which sport?
Squash.
Squash. Okay, squash would be, I mean, that's of the tennis family.
Yeah. And golf.
And golf. Well, I did send did I send the link to everybody about the Miller Lite commercial? I want to watch football, I want to watch golf, let's watch both. Yeah, so yeah, you can link, I think, tennis, I'm sorry, you can link football and golf. I'm not sure if we can get to tennis.
Via the Miller Lite.
Via the Miller Lite. So in a situation like this, imagine that you're a little bit worse than the other team. So your one is a little bit worse than their one, your two is a little bit worse than their two, etc. Then when you play something like this, odds are yes. So if you're a little bit worse, when you have a matchup like this, you're in trouble. So what some teams do is they do 1 versus 5, 2 versus 6, 3 versus 1, 4 versus 2, 5 versus 3, 6 versus 4. This is not honorable. You are supposed to be honest about who's your 1, who's your 2, who's your 3. So why might a team lie? To win. So if each one counts the same number of points, then by doing something like this, you're basically sacrificing the first 2. And the hope is you can win maybe the last 4. So this happens sadly all the time. Did you ever have this happen to you?
So we didn't really have a coach for a squash team, so I was the coach and I was stacked 4 or 5.
Okay, maybe I should not be recording this. So,
but nothing blatant like that.
Well, so what often happens is it becomes very clear immediately that when you're the number 1 and you're playing what's supposed to be their number 1, and you see this is not their number 1. And so, various teams have different levels of honor about how they would do something like this. But, again, if you're a little bit worse, the standard straight up match is going to be terrible for you. So my question is, imagine you actually know that the other team is going to pitch, 1, 2, 3, 1, 2, 3, the order of their top 3 pitches. Do you want to align yours to go, you're 1 against their 1, you're 2 against their 2, you're 3 against 3, or do you want to maybe sacrifice, put your 3 against their ace, essentially concede that game and try to win the next 2? And then this could be a function of how many days off do you have between games, how long the series is. If the series is, best of 3 versus best of 5 versus best of 7, how does that influence your strategy? What we could do is we could do something, very similar to using, the Bill James, log 5 rule, which I talked about, to try to rate what is the probability that you win or lose a different match. And so if anybody is interested in, a quick fun research project, I think this one would be, really interesting. I don't know if anybody's looked at this yet in terms of just what is the advantage and how much of a difference do you need for this to matter? Who is the most famous Jewish pitcher of all time? very famous for not pitching on Yom Kippur. Anybody know? Sandy Koufax. And so it was game 1 of the World Series, and he told his manager, it's Yom Kippur, I can't pitch. And he became an instant hero to huge numbers of Jews. My great uncle may be best happy today that the Yankees have been eliminated. He had a son who was a huge Red Sox fan, and he invited Sandy Koufax to his bar mitzvah. Sandy Koufax didn't come, but he did send a nice letter. And so the manager said, okay, so I pitched Koufax in game 2, and I thought Don Drysdale in game 1, this is not a big deal for me. He was lucky to have 2 good starters, so it didn't really make much of a difference for him. But you could be in situations where it does make a big difference. Allegedly, Drysdale had a horrible game, and they lost game 1. And allegedly, Drysdale said to the manager afterwards, "Bet you wish I was Jewish today too." But anyways, if you're interested in this project, let me know.